So this was the exercise. Why this circuit of swaps? Because maybe it's complicated to experimentally create an interaction between distant qubits. And this is a circuit which will show that it's only of linear depth and will allow us to have each of the qubits adjacent to the rest of them at least once. And the idea is if we have this kind of interaction, which commute with the other terms, no? Sigma set commute with sigma set, then we can wait until the qubit is close to the qubit we want, and then apply the interaction. And then continue with this circuit of swaps and apply the interactions intermediately. This would be the idea. It's defined for the lattice here, but we are going to give the results for a given square lattice. And also I have to say, if you are interested, there are similar things for a linear array. But we are not going to discuss now, but it's very similar, it's the same idea actually. And also, maybe some disclaimer is that we are not going to give the formal proof in terms of graphs or anything. It's on the paper, on the reference of the paper that I'm going to put, because this is taken from a paper. And the formal proof is only for n a power of 2. I don't know if it extends to other numbers of qubits, but in this case, we'll see how it works. Okay, so the first, we are going to understand all of this that I was saying before. Give the first layers of gates. So we are going to give them. We should think of the gates maybe somehow in 3D. Like if this is a line coming from its qubit, we will apply something here in the yellow parts, and then we build on top of that and things like okay, then the first step, we have already done it. We have defined a closed loop. We can define the closed loop that we want. And then once we have the closed loop, we can define the left stagger and the right stagger, which are just two disconnected graphs that we have defined with the yellow and purple, that are, maybe you cannot see it very clearly, but it's yellow, purple, yellow, purple, yellow, until the end. And then this is the circuit. So I have here a bit bigger. These are the labels of the qubits, and we are going to apply swap gates. So the idea is now that we are going to apply this set of gates until the qubits return to their original position. Let's see what it means. So first, I didn't say it before, but this color that I was forgetting to mention is like we can color this as if it were a checkboard. And then let's do that super quickly. Maybe pink and green. So, yeah. So if it is a checkboard, it's like this, no? Pink. And actually it's pink and empty, because I don't want to color the others. But now we have some identification here. This is also imaginary. Now we are going to apply this kind of layers. So let's apply the left. When we apply the left, it means that we do, the left was the yellow. So we do a swap gate here, 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 here. This is the UL. Actually, yeah, let's think that the initial state is here, kind of, okay? Input, and then we do this, and then we do this. So it's the opposite as applying to. Okay, when we do this, qubits swap. So you'll see that they will change, the peak will be now there, and so on and so forth. So now, after this is applied, we will have something like this. So we have, let's erase what we have here. And also the colors will swap, right? So the one is the pink and so on. So the idea is that you can imagine this as some of the colors going in clockwise direction in the loop, and the other colors going in counterclockwise direction. Because now if we apply the UR, it will be a set of swaps here, 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 and here. You can follow the colors again, and now it's going to be. You'll see that the 0 will travel to this side, the 2 will travel here. So the pink ones are traveling in this direction, and the others are traveling in the other direction somehow, by sequences, by sequences of these layers of swaps. This is more or less the way I understand it. I think it's clear. So shall I apply the next one just on the first one, so that you see that the 0 will now come here, and then the 3 will be there, and we do the same for the rest. I'm not going to do it, because, but you see the idea? You see that the pinks will go clockwise and the other will be counterclockwise. So the thing is that we apply this, doesn't matter how we start, certain number of times until the 0, until they return to their original position.
But then you haven't done anything, right?
Yes. You have, for example, now the qubit 0 would be close to the qubit 3, and before it wasn't. So the idea is like, at this point, you can maybe, if you have this interaction, you can apply the interaction between 0 and 3.
Okay, sure, okay, so you will, because I think as I understood it, you're gonna do left and right swaps until you're back in the original state.
Yeah, this is the thing, because you want them to be adjacent to any of them, but the idea with this kind of interactions is that you interpolate some of the interactions that you want to interpolate.
Yeah, but it means that you're doing like UL and UR once, and then you do some interaction, and then you do UL and UR again, right?
Yeah, exactly.
Oh, okay.
So that you find several configurations, and after you go through all of them, they are close to each of them. Not to each of them. We haven't finished. So the pink one, the pink here, would be close to any of the non-pink. But they will never be close to a pink one.
Yeah.
That's why we have to repeat it.
So then I think maybe this is a bit confusing. Step 2, so it says alternate layers of swap gates on
the left stagger, so the idea is like, imagine that this is a 3D, no? This is your layer, and now the first thing that you do is like, first thing is check, do I have an interaction with this configuration and this labeling? Yes, no, I apply it, no. Second, I apply the left stagger. You apply it, in parallel, so the depth is 1. When you apply UL, is 1 because you can do it in parallel. We are going to, the overhead is for the depth. And then you will have other configuration of qubits. So the qubits will be adjacent to other qubits that before they weren't. And now you see, do I have anything here? Shall I apply the interaction? No? Okay, next, the right. you apply the right.
Okay, so but there's no operation that is like acting as interaction.
Not now, but the idea, I am only going to give the circuit such that all of them are adjacent to the rest at least once. The idea is that when we have these kind of things, you interleave that. But this circuit is, of course, is doing nothing. It's going to the original position such that every of them have been close to the rest of these ones. This is the only point. But yeah.
Did you say how we were going to get the red ones to be close to each other as well, or?
We are going, it's on the steps,
Okay.
but we are going to see it now.
Okay.
So the first step, the step 2, we have done it. We have had all the pink ones close to the non-pink, right? But that doesn't mean that everything is close to, everyone is close to everyone. Now the third step is going to separate the pink and the non-pink in the following way. So once we go back to the original position, still it will always be a checkboard. It will be always in a checkboard manner, right? Sometimes the pink will be here, sometimes here, or whatever, but they are always going to be like white, pink, so on. Now the third step is alternate between two staggered layers of parallel swap gates to move all the colors to separated sides. What does it mean? I'm going to give you the particular example. So for example, we will be in the original. It's right here, 2, 3. These parallel swaps are going to be this. So first we do a swap here, and the idea is that I want all the pink ones in this side and all the non-pink in the other. So since I want all the pink ones in this side, I'm going to move this pink here, I'm going to make some space to move this pink there. Also I want this pink to come here. Also this I want it to move here, and this also here. So actually I'm going to make this, and this. These are the swaps that I'm going to do now. The purpose is I want all the pink ones to one side and all the other to other side. This is one. I still need to do a second layer to have all of them. So if I have that, I will just have the one here. I'm going to have it in pink. The 6 here. The 4 here. The 9 here, 14, and the 12. I'm not going to write the number of the rest, okay? Just I'm focusing on the pink, but the rest are white, and I don't care about the number. This is one layer of swaps, such that they end in this way. So I only have 2 left to move to this side. So the last swap layer would be this and this. So in that way, all the pink ones would be in this side. I know it's a bit of a mess, but all the pink ones after this would be here, and all the white would be in the other side. After this swap, so this 4 is no longer here, and this 12 has moved here. done the step 3. To separate the colors in different sides. Step 4, repeat 1 to 3 for the divided sectors. What does it mean? So 1 would be like define a closed loop, blah blah blah. Define a closed loop. So I define this closed loop. And here also define the closed loop. I define this closed loop. And then we will define left and right scatters again for both subsets. And then are disjoint graphs. So then the disjoint graph would be, as we saw, like some yellow, and then purple, and then yellow, yellow. And the same for this, it's exactly the same. And actually we can do the things in parallel. And then what we are going to do once we have defined that, we do the same. We alternate the layers of swaps, and you will see that, and also we will have some checkboard coloring here, so the same, like non-color, other color, non-color, other color. So we apply the same thing on the subsets, and then we will apply the swap gates, as we did before. So each of them will be close to the other color ones. So here, for example, I will have some green, non-green, green, green, and all the green ones will be close to the rest of the white ones. And the same here. We define 2 sets of UL and UR, let's say. But we can apply them in parallel. We have, these are not connected. Okay. And then we do that. Then all of them will be close to the white ones, and here the same for the colors you will choose. We'll see again, do we have some interactions to apply here in the middle, what do we do, blah blah. And then we finished. And then the last part would be again the same. Still we haven't, the green ones haven't interacted among themselves, so we need to apply to separate the colors. We will separate the colors, for example, I want to bring the green ones here, down. So I will apply here a swap, and here a swap, and here. And then I still need to apply one more. So I'm bringing this down. And then I do the same. And now when I have 4 qubits, it's already done. You make them interact with all of them. Yes, so now, is this more or less clear, the process on how we do this? Okay.
Now, the objective of this is just, if you have this particular connectivity of qubits, you somehow want to implement this interaction which couples each and every qubit. And the way that you do it is just by weighting or the
Yes,
swapping
yes.
and weighting.
Because imagine that you would do, like, compare it with the most, let's say, without approximating anything, right? Oh, I have an interaction between the 0 and the 15. In general, you need to do how many swap gates of the order of n, actually, in this case. N gates to move this close to n?
Yeah,
No, square root of n.
because if you can start half from that side, half, half
Of
from
the
this
order
side,
of one of the sides, right?
yeah.
And then you have to go back. And then you will have to do other interaction. And then you will have to. So the
okay, so
overhead is very large. While here, you see that it's going to be only of this order because we are going to see it now.
I guess this is sort of a general recipe. It could, for a particular problem, there could be a better strategies, I guess. Yeah.
I guess so, and actually I think it only works for this kind of Hamiltonians. Because imagine that it does not commute, then you cannot choose any particular
Sure.
order.
Yeah, I was thinking more like, if you don't have all-to-all interactions, it might be so still a lot of overhead to go through all this swapping.
Mm-hmm.
Because it could be that if you only have a few long range, it could be faster to just do swap gates between those two pairs, right? Like,
Yeah.
this method will not always be better. It depends
No,
on
no,
which J terms are 0 or non-zero.
no. They are not claiming, I think, I haven't read the paper super limited, but I think they are not claiming anything that they are optimal. They claim this over here.
Yeah.
And then it's for this particular of lattice set. I think you can extend that to rectangular. I think that in the proof it was restricted to that. I will need to double check that, but I think this was the case. So yeah, if you have other connectivity and a particular problem, it might be that you have a better solution. This is true. I think there are no optimal ways of doing things.
It's
You
like
just
some
can
kind
claim
of
some
compilation.
overhead. Huh?
It's like compiling your algorithm actually with the hardware.
Yes, I mean this assumes like what would be here the compilation. It assumes that you can have these kind of gates, but they are not exploiting all the gates, no? Because once you define the closed loop, well they will be exploiting in the sense that later we will define other graphs and everything. And they assume a general distant interaction between qubits. And then they assume this kind of, this would be useful for this kind of Hamiltonians where you have the terms commuting with each other.
Yes, with an odd number of lattice sets, you can't define a closed path, so this doesn't.
Yeah, right? In the sense that you cannot end with how you want it, no? With these disconnected graphs. The formal proof is on the appendix of the paper. This is also on the appendix on the paper, so you can have a look if you want. But I'm sure it assumes that when I look at it tomorrow. I didn't want to go through the formal proof because I think like the visualization is easier to understand the trick. And then I don't know how much time we are going to show that. It ends at 3?
Yes.
Yes.
Ah, okay. Then we will have plenty of time. Laura?
The square of n means that we need to do this many times of operation to get the situation that we want. The square of n gate.
You mean this?
Yeah.
This is just, for example, if you want to do a swap and go back, of the order of how many gates you need if you are not using any circuit of swaps or anything. And in general, let's assume that it's of the order of one side of the lattice or something like that. You can, no? Like 2 square root of n or something like that, gates, no? And then you can count back, but it's of this order. Yeah.
Maybe I remember wrong. You said that this is better.
Ah, no, yeah, this is, no, but okay, this is only for one interaction. But imagine that you have to do it for any kind of, I don't know how many interactions of this kind are n over 2, right? Binomial. So it would be of the order of, I'm doing this correctly, something like this. Yes, no? No, I am not sure. So it's of the order of n squared interactions that you would have. So imagine doing this for n squared, like it's
I guess you've kind of already proven that an even by even rectangular grid should be able to be subdivided into something that will go down to a 2 by 2 case.
yeah, and in the end you end with just the 4, no? So
So
imagine.
it should hold for more than just square grids. It should hold
Yeah.
for rectangular grids as well, as long as the edges are even.
Yeah. It's for rectangular. The only thing, I think the only requirement is this, the power of 2.
The total number of.
Yeah, the total number. So then in the next step, we do all the steps here. We have all the greens here, down, and then we define a closed loop. And we extend again the checkboard thing. We do the interactions, and then when we have 2 in the end, we have finished, because then we can Now we have seen this for 4 by 4, but let's see what is the overhead on the circuit there. If we have square root of n times square root of n. So, can I erase here? Is there any question? Because we have time. We have
Yeah, is that easy to create this loop? Because it seems we need to have a lot of layers so that, or loops so that we can have that into.
Yeah, you need to create as many loops. We'll see how many times we have to go through all of this in a minute. But yeah, you will have to create as many loops as. So when you arrive to 4, you can make interact this with these other 2, and then you will need to be able to make this interact with this. So that's the n part. We are going to see that it's of the order of logarithm of n steps that we need to do. But you need to define a closed loop. It doesn't need to be this loop, right? It's just a closed loop. So that then we define some UL and UR disconnected. So we apply first one. We cannot apply them at the same time because they are acting in the same qubits. But they are disconnected. So, but we can apply in parallel all the swaps in UL, in parallel all the swaps in UR. And then, yeah. Then you have other configuration of the labels. And then you see what if you apply some interactions or not. And you do sequentially until in the end, in the very end, then you see that I don't remember the colors. All the pink were interacting with all the white, but not among themselves because they were traveling in one direction. They are never close to each other. And then when you divide it, then you will make some of the pink close to other pink because now you define other colors here, and you will do the same. You will do the same until we finish, no? With all the qubits being close to all the qubits. So I think that the ending is when you have 4 qubits or 2. 2 qubits. Exactly. So when you have 2 qubits, it's like I'm finished. I don't need to do any swap. I've ended this. So there is a nice trick that might be useful for some things. Let's see. Maybe I erase there. And let's see how goes the overhead discounting. So now it's so that for n qubits the number of the depth of the circuit is of this order. Where the depth is not the number of gates, but the number of well, okay, we will have some kind of thing like this, and we imagine the layers in 3D. This is the first layer of gates. I don't know. You imagine this is one layer of gates, and then you have more layers of gates, and this would be of the order of n layers. Okay. Now let's see. If we have an n qubits here, this would be of the square root of n, it's minus r squared. Okay, how many times do we need to apply UL, UR in the beginning? It's going to be of the order of n over 2. Because we want them to return to their original position. And if we have to implement them n over 2, this circuit in total has the n. No? 1, 2, n over 2. We see this. Like, if imagine that the qubits are traveling clockwise or counterclockwise, however you want, and then you count how many layers you need to do, and it's going to be that. It's going to be n until they return to their original position. Okay, this is in one cycle of the steps. Now step 3. This is maybe a bit more complicated, but to see, but we'll see now. Step 3. This is for step 2. Step 3 will require a square root of n over 2 cycles at most, in the worst case. Why? There is a way of thinking about it. So remember that we have a checkboard situation, and we want to move all the colors to one side and all the colors to the other side. So in principle, we will need to implement how many, there were disjoint swap gates, no? And how many swap gates do I need to implement? So I need to move them to one side. So I would say that of the order of the half of the cycle. Mind that there is one that is very far here, and then I want to move it here of that order in the worst case. This number of cycles. For step 3. So, and then after the step 3, we have to repeat this thing of defining the closed loop certain number of times. And then how many? Huh? It's a logarithm, but it's a way of seeing it. This, like, for example, it's like we end when we have 2, right? And we divide the number of qubits several times. So we have, for n steps, we need to reach kind of, this is the way I think it. I don't know if this is a 2 or a 4 now, I don't see. But if you see,
Some number.
yeah, some 2, it doesn't matter because it's the order with the, we see. Yeah, we stop dividing the loops when the number of qubits is of the order of 2, right? Because that's when.
I mean, you can also think of this as like a binary tree. You start with n, divide 2 times, and then divide 2 times, and you end up when you have no longer any 2 things to divide. And the number of steps that you will do this is usually is log of n.
Yeah, this is I have never thought of it that way, but it's a nice way of seeing it also. So here we see that n, it's on the order of log n. I don't care about exactly what order or anything. You can think it as Sanavas was saying, or you can imagine like, yes, how many do we need to do? Yeah. Log n. Log n what? Repetitions of step 1 to 3. And then we can see now what is the total gate there. Would be something like that, no? We have some k from 0 to log n of what? Which is of the order of n. Why this? Because in each cycle we are considering n over 2 qubits, right? That's how we implement it there. So for the next cycle, that instead of to the depth n/2, and so on and so forth, and this is here. And the same for this n/2 here, and for each you will have half and half and half until you n. And this is of n. I ended before I.
It still seems like a lot of overhead if you have to consider what the actual fidelity of any individual swap is. Like, it doesn't seem like you would reasonably expect to get anything useful out of doing this procedure. Like, say you have 99.5% fidelity on every swap operation you do, then if you start going above, like, even to a square lattice of like 2 by 2,
Mm.
it becomes almost
Yeah.
intractable.
Yeah, I mean, like if you compare it with the usual trick of going back and that, you clearly gain in the scaling. But I don't know for actual devices.
But like if you want to actually implement it physically on a device, I don't think you should expect, if you want to put every qubit in contact with every other qubit, that you should get any result out that makes sense.
What's your alternative?
Yeah,
I mean, it's not a problem of this,
Yeah,
this
yeah.
algorithm, right?
It's more a problem of is it useful from a this help us with algorithms
Yeah.
problem?
Yeah, I think that. So, how many layers can you implement experimentally now? Here, this day.
I mean, what would it be for, say, 4 qubits or something like that? We could calculate the number of layers and then.
There is some quantum volume, no, that you define as.
Then you're counting the number of swap operations, so then it's just your fidelity times the number of swaps you have to do.
Mm.
So let's say you have to do like,
It's 3 2-qubit gates per swap,
let's see, you get the swap operation.
which no one has.
Ace can do it as well.
No, you need 3 R swaps to do a swap.
Yeah, I mean, yeah, maybe it's not implementable.
I'm
Maybe.
sure it's implementable, it's just a matter of
Yeah, maybe
where's the
depends.
trade-off.
Yeah, it depends on the problem, right? Maybe you would like to. Maybe there are optimal strategies for certain couplings here. This is of course assuming that you have the worst case, 9 all to
Yeah.
all.
Yeah.
Then this would be really nice because at some point you will have all to all. But maybe this is overkilling for some
Yeah, I
I
applications.
think so, if you have very local sort of or sparse graphs, then try to put the qubits that are very close to each other, so you only need to do a few swaps between them
I
and
see.
so on. But, so yeah, I think it just needs to be, this is what a compiler needs to do, it needs to take, okay, and figure out which qubits, like how to map the logical qubits to the actual physical qubits in such a way that you reduce the number of the swaps needed in these things.
Yeah, I see.
Which type of problems would require an all-to-all type coupling, like VSAT or?
It depends, no? Like, for example, if you have MaxQt,
Sure.
it depends on the kind of graph that you have. But imagine that it's a super general graph, very complicated, that you cannot classify in any subgraph set. And then maybe this would be an example. And this is typically where MaxQt is NP5, and is NP complete, I think.
The decision problem.
Yeah. So yeah, this is one example I can come up with, but there are more cost functions defined on the lectures. I was not going through it because I had the impression that Julia had gone through all of that, but it's really on the lecture. It's not difficult to define a cost function. And then, yeah, for example, MaxQt. And I think that you can reduce many problems to MaxQt. Since it is NP complete, basically, no any other NP problem can be mapped to that.
So moral of the story, there is no all type problems.
It depends on the specific optimization, right? Like for example, for real problems, maybe I don't know what is exactly the shape of the cost function, that Pontus can tell you about the scheduling problem in particular or things like that. But in general, I think it's all to all. Or, yeah.
Yeah.
Of course, maybe there are some things that you can do on the Hamiltonian. Instead of having the perfect cost function, maybe you can have make some manipulations here for the QAOA or the optimization problem.
You can also say like, if there are some terms that are quite small, you know, it might be better to just put it to 0, because that would be a better approximation than try
Yeah.
to use the
But then you are already manipulating at the level of defining the problem in the cost function. So yeah, there are several things that you can do.
Because you know that if my fidelity to implement the interaction is 99%, if the interaction is then smaller than 0.01 or something, it doesn't make sense to do it.
Yeah, I think it's already the time. Yeah.